Okay, and the final talk of this session will be Sonia Reilly, who is studying mathematics at New York University, and she also did her practicum at Lawrence Berkeley National Library.
All right, thank you for the introduction. So jumping off that question about inverse problems, I'm going to talk about some research that I've done in the last year or two on Bayesian inverse problems. So there's a lot of words in this title, so let me break this down a little bit. Let me start by defining the kind of problem I'm working on, which are hierarchical PDE-governed Bayesian inverse problems. So first of all, if any of you aren't familiar with inverse problems, these are a kind of problems where we're trying to find some parameter of a system. I'm going to denote it as m of x because I'm typically interested in function-valued parameters. And I'm trying to find that parameter from noisy measurements, which I'll call y, of the solution of a PDE. So my data is going to take this form of like yi, which is the solution, which can depend on my parameter m and also some other parameters theta, evaluated at various points xi with some noise added, where again, u is the solution of some PDE, which involves m and maybe theta. So what I'm trying to do here is to infer a discretization m of this function m of x with its uncertainty, and that's where the Bayesian component comes in. I'm trying to compute a posterior distribution using Bayes' rule. So Bayes' rule will tell me that the posterior distribution, I'm going to use pi to denote distributions throughout the talk. The posterior distribution of m and theta, conditioned on y, is the product of my priors of theta and priors of m given theta, which are sort of encoding prior information on what I think the distribution of theta and m might be, times the likelihood, which is the probability of y given these parameters, is going to give me this posterior distribution up to some proportionality constant. So Bayes' rule gives me this posterior in m and theta, but I'm really interested in m, and theta are going to be some other parameters that I'm less interested in. So the last thing I want to do is marginalize over these hyperparameters theta, meaning integrate them out to sort of average over these things that I maybe care less about and get a distribution over just the m that I care about. All right, so Bayes' rule gives me this posterior, so what's hard about this? Really, the challenge is that anything I might want to do with that posterior requires integrating over m. And m is high dimensional. It's a function. I care about the discretization, so it can be arbitrarily high dimensional. And then if I want to normalize, if I want to find the mean, if I want to find the covariance, any of those are going to be integrals over m. The straightforward way to do this might be something like numerical quadrature, but obviously that'll suffer from the curse of dimensionality. So if I choose a high level or a fine discretization, numerical quadrature will really struggle. There are various methods that people use to get around this. By far the most common is MCMC, or Markov chain Monte Carlo. That one also struggles in high dimensions, so it converges often prohibitively slowly. Another strategy that people use is variational inference, which, unlike MCMC, is a deterministic method, but it's limited to approximating your distribution in particular families of distributions. So what I'm going to talk about in this talk is a method that avoids some of the pitfalls of MCMC and variational inference, with the trade-off that I'm going to make a few assumptions. So here are the assumptions that I'm going to make this more tractable. So first, I'm going to assume that my hyperparameter theta is low dimensional. So I'm going to lump in any parameters that I care less about, maybe hyperparameters of the prior, or any parameters of my model that I consider sort of nuisance parameters, into one vector theta that I hope has less than about 10 parameters. The other assumption I'm going to make is that my prior for m is Gaussian. So this is maybe less of a strict assumption than you might think, because the prior is something I choose. So I can just choose it to be Gaussian. And then with these two parameters, I can pose my problem as a latent Gaussian model, where theta follows some hyperprior, pi theta. M has a prior conditioned on theta, which is Gaussian, depending on this theta. And my likelihood is some distribution depending on this forward model u, and potentially also on theta. Okay, so for this case, for this latent Gaussian model, there's a method that's become increasingly popular over the last 10 or 15 years in spatial statistics called INLA, or integrated nested Laplace approximations. This restricts our scenario down to latent Gaussian models, and it also makes one more trade-off, which is that it approximates the probability of mi given y. Mi being like an evaluation of m at a particular point xi, or a coefficient of m, if we're doing like a finite element discretization. So basically, instead of approximating my full distribution of M, I'm now making the trade-off that I'm going to approximate point-wise distributions of M at specific points. So if I can make this concession that I'm going to find one-dimensional distributions, and I can make assumptions that make this a latent Gaussian model, I can apply this method, which has several pros. So it's deterministic, unlike MCMC. It's not restricted to a family of distributions, unlike variational inference. And it's been a fast and typically very accurate method in the field of spatial statistics. The cons are that it does not give me the full joint or a good approximation to the full joint. Sort of looking here on the right, the full joint would be this sort of contour plot that we get from Bayes' rule. And what I'm really going to get out of INLA is this green plot on the left, which is just projecting out the dependence on theta and projecting out all the other m's. So again, I'm only going to get one-dimensional distributions from this. And the other con that is in bold here, because it's what I'm going to focus on for the rest of the talk, is that this is a method that's been used typically in cases where the forward model is very simple. So often it's as simple as just an identity map. And I'm more interested in PDE cases. So I'm going to talk about how we might be able to extend this to PDE problems. But first, let me give an overview of how this method works. So at the highest level, I'm going to break it down into 3 steps. The first, which I'm calling step 1, is to approximate the hyperparameter distribution. So these are my hyperparameters or nuisance parameters. I just want to find the distribution of those, marginalizing out M. And then in step 2, I'm going to approximate the conditional distribution of my mi's, given that hyperparameter and y, for any points I that I'm interested in, and then at some set of quadrature points. And I'll talk more about how to find those. Then finally, I'm going to compute the distribution that I care about, this distribution of mi given y, for any I that I'm interested in using quadrature. So the distribution of mi is this joint of mi and theta, integrated in theta. And I can take that integrand here and just use basic conditional probability rules to split it up into this conditional probability and this marginal probability that are exactly what I got from step 1 and step 2. So I just plug these values in from above, and then I get an integral over theta. And again, I made this assumption that theta is low dimensional. So this is an integral that I can actually just do with quadrature. All right, let me step through these in a little bit more detail. So starting with step 1, I want to find the marginal distribution of theta. This is a high-dimensional integral, because the marginal distribution is this joint of m and theta integrated in m. And this is exactly what I was trying to avoid in the first place. So how am I going to do this? By approximation. So on the right, you see something that I might be trying to approximate, this pi of theta for a specific case. Let's see what happens if I make this sort of stupidest possible approximation. I take my joint in m and theta, and I find the closest possible Gaussian to it. So I find like a maximum point, and I do a little finite difference there, and I get a Gaussian approximation. And then I integrate that, because that's easy to integrate. The marginal of a Gaussian is a Gaussian. The problem with this, of course, is that then I'm restricted to Gaussian approximations, which since my black line here that I'm trying to approximate isn't very Gaussian, that's not a good approximation. Well, what I'm going to do instead of this is use the same Gaussian approximation idea and use it in a more indirect way to get a much more accurate approximation. So this is what's called the Laplace approximation, or depending on the literature, sometimes either of them can be called Laplace, but I'm going to choose to call this one the Laplace approximation. And the idea here is that I'm going to rewrite my marginal distribution of theta as this full joint of m theta and y, so both parameters and the data, over the conditional probability of just m. And this is just using conditional probability rules. Then I'm going to take the denominator here and approximate that as Gaussian. There's actually a good reason to think this might be close to Gaussian. It's going to be exactly Gaussian in cases where the prior is Gaussian and the problem is linear. I already assumed the prior was Gaussian, so if my problem is linear or maybe close to linear, then this would be a pretty good approximation. And then this, we can plot for this little example I have here, and that's going to be this green dotted line. You might not even be able to see it in the back. That's because it's very, very close to the black line. So this is a much better approximation. And this is sort of the trick that I'm going to use throughout this method for getting rid of high-dimensional integrals. So that's step 1. Step 2 and 3 together we can look at as doing this low-dimensional integral to get the distribution of m that I'm interested in. So I wrote this up in the previous slides too. This is the joint distribution of m and theta. I split it up into what I found in step 1 and now this distribution of mi, and then I'm integrating in theta. So there's two things to do here. I have to pick quadrature points in theta, and I have to approximate this mi. So first picking quadrature points. This is the same plot from before, but now this blue curve here, this marginal in theta, is what I've computed in step 1. And I can do a very simple kind of quadrature here because I'm already making other approximations. So I just do a very simple thing where I find the maximum point of this using some kind of optimization method. And then I do some little finite differencing here to sort of get the standard deviation or approximate standard deviation, and then just step out to the left and to the right until I get to a point with low probability. Then for each of these quadrature points, I take sort of a slice through this diagram, meaning a conditional probability conditioned on each of those thetas. And I integrate those together, left to right. But there's sort of another high-dimensional integral hiding in here, which is that I am integrating out all of the other mi's. So I want the distribution of just one mi, and for every other value, I'm integrating that out to get the marginal of just mi. How do I do this? Exactly the same as step 1. So I could just do a Gaussian approximation, or typically I do another Laplace approximation, and that's where the name of this method comes from. So that's the second nested Laplace approximation in this. Yeah, and then I do the quadrature to get this distribution that I'm looking for. So that's sort of my overview of how INLA works. But now I'm trying to use this for PDE-governed problems. What are the challenges of that? So in classical INLA, this is, like I said, typically used for cases with simple forward operators. And it's fast because the computational cost is dominated by inverting large matrices, and we can do that with some speed by using sparse linear algebra. In my case, those kinds of speedups don't apply because we have a complicated forward operator. It's going to be a PDE operator. And so the computational cost is not dominated by inverting matrices. It's dominated by forward and adjoint PDE solves. The other downside is I can't build any of my matrices explicitly. I'm going to treat my PDE solve as some kind of black box finite element solver. So I can't use any of these tricks with sparse linear algebra. So what am I going to do instead? I'm going to go over this very quickly because this is sort of the more technical part, but this is what I've been working on a lot over the last year or two. The key insights that I've used to make this fast are that for PDE operators, the precision update, meaning the posterior covariance, the inverse posterior covariance minus the inverse prior covariance is a low rank operator because of basically smoothing properties of the PDEs I'm using. So that update is something that we can pre-compute using randomized numerical linear algebra and then store a low rank approximation of that rather than having to go back to the PDE every time. This basically has the result of not having to apply the PDE over and over again and just having a low rank approximation that we can use instead, which is much faster. The other insight is that there's something unique about PDE problems, which is that we can use different kinds of meshes to make it either fast and more approximate or slower but more accurate. So we can use a multi-level approach, which is to use a coarse mesh to quickly find the quadrature points for all of those computations that go into that and all of the optimization that we need to do to find the maximum point, and then use a finer mesh in the last step where we care more about accuracy to get our distribution of mi. So let me just talk about a quick example to hopefully make this make a little bit more sense. So this is the problem I've been working on to sort of test this, which is an initial condition inference problem in advection diffusion. My forward problem is that I have some initial condition U0. I'm going to use it as an example that this is like a chemical concentration in space. For example, like some chemical contaminant has been released in a city. Down here, this would be the yellow spot. The white are, for example, buildings that are cut out, so cutouts from my domain. And then from that initial condition, the forward problem is to find the full distribution of U, or the full function of U over time and space. So running the forward problem, we start with this initial condition, and then over time, this chemical contaminant advects and diffuses around the city. The inverse problem then is given data, so given measurements of the chemical concentration at various different points in space and time, with some Gaussian noise added, I want to find the distribution of the initial condition given my data. So that's the inverse problem. What are the hyperparameters? What's hierarchical about this? So the hyperparameters I'm going to choose, and there are many options, are gamma and delta parameters in the prior covariance. So in latent Gaussian models, my covariance, or my prior is always going to be Gaussian, so it can be described just by a mean and covariance. I'm going to use a Gaussian random field with a fixed mean, and the covariance is this PDE operator. Choosing a PDE operator makes it very fast to evaluate. And gamma and delta here, basically their ratio determines the length scale of the prior. So on the right, I've done step 1 here of my algorithm. I've found the distribution of gamma and delta, which together make up my theta hyperparameters. And so we get this distribution here. And then we can do that finding the quadrature points that I talked about, where we find the maximum point and then step in various directions until we get to low distributions, or low probability. And then step 2 and 3 are finding the distribution of the initial condition from that. So I've shown 2 here just as an example, but I could do any point in space here. This is my true initial condition. I've chosen 2 points here. The first one is this red circle up here. This is my final answer distribution over that initial condition at that point. The red dotted line tells me the true value, and this black curve is my distribution. Same for this point out here with lower initial condition over here. So we can tell that we're picking up more or less where the true value is with some measure of how much uncertainty we have. Just to wrap up very quickly, in conclusion, INLA is a fast and accurate method for computing specifically point-wise uncertainties when my hyperparameters are low-dimensional. And the key to how this works is to use Laplace approximations for high-dimensional integrals and quadrature for low-dimensional integrals. And what I've been working on is to adapt this to be fast for PD-governed problems. I just want to conclude by thanking my group at the Courant Institute at NYU and CSGF for this opportunity.